Hello everyone, my name is Mudasar Khurshid and I am doing MSc in Polymer Process Engineering from UET Lahore under the supervision of Dr. Yasser Gill. Today I will be presenting the effective polymer processing techniques for plastic part production using nanofiller. So let's start. Plastic waste is a representative of a waste product that originates from industrial development and its discharge to environment causes severe environmental problem. Currently, plastic products are an essential part of people's daily life and are applied in various industries such as construction, healthcare, electronics component, agriculture, and automotive. The demand for plastic continues to increase due to excellent advantages of plastic such as convenience, durability, resistant to erosion, ease of processing, and low cost. Global plastic production has grown at a compound annual growth rate of 8.4%. The annual plastic production was 360 million ton in 2008 and plastic production is estimated to reach 50 million ton in 2025. Only 9% of plastic are produced have been recycled. The other fractions of plastic waste are either incinerated or landfill or lost to the environment. According to an estimate, 12% waste is incinerated and 79 is ends up in landfill. The demand of plastic mainly comprises polyethylene, polypropylene, polyvinyl chloride, polyethylene terephthalate, polyurethane, and polystyrene. Polyolefins such as polyethylene and polypropylene are the most demanding plastic throughout the world. Packaging industry consumes the highest portion of plastic products and it is major plastic waste source because of the well-known application of disposable products. Plastic waste undergoes slow degradation and can remain in environment for at least decades or even hundreds of years and cause serious environmental issues. These practices of landfilling and incineration is huge loss in terms of valuable material and energy used to make plastic products. It is necessary to decrease the environmental impact of plastic waste and to adopt the circular economy to replace the current linear economy. In a circular economy, products and materials are being reused, refurbished, or recycled according to the waste ladder, instead of being incinerated or disposed. Plastic waste can be divided into four classes: primary recycling, secondary recycling, tertiary recycling, and quaternary recycling. Primary recycling, also known as closed loop recycling, is a process of taking uncontaminated discarded plastic and turning directly in that material into the same new product, ideally without loss of properties. A familiar example of this would be to use a clean aluminum pipe and use the metal to make a new aluminum pipe. Secondary recycling refers to the mechanical recycling, where the chemical identity of the polymer is unchanged, but the polymer is in some way physically reprocessed and generally used for different purpose than its original use. An example of this is taking the waste tire and using the rubber crumb as addition in rubber flooring or park benches. In tertiary recycling, waste plastic is used as a feedstock in process that generate chemicals and fuel. An example of tertiary recycling is the glycolysis of polyethylene terephthalate into diols and dimethyl terephthalate that can be used to make virgin PET. In quaternary recycling, energy is recovered from waste plastic by incineration. Dried fuel is an example of quaternary recycling. In the context of polymer, the most prevalent problem with primary and secondary recycling are related to the stability. As the polymer are continuously reprocessed, the polymer may degrade to different extent, which will have drastic effect on the mechanical properties of the post recycled product. Additionally, the need for pure clean plastic waste is a significant barrier when post consumer mixed source plastic is targeted for recycling. From environmental point of view, mechanical recycling of waste plastic is considered the preferred option. Despite odorous emission released during the meltdown of waste plastic and soil contamination which affect environment and human health, mechanical recycling is generally environmentally friendly approach for waste plastic disposal. Persistent organic pollutants can be released from energy recovery, which would damage the environmental performances of these processes. Besides, there is a lack of commercially successful energy recovery of operations due to technological limitation, operating cost, and variable quality of feeds. Moreover, no energy recovery method offer a net positive energy balance. Generally, recycled plastic can be regarded as renewable source of material, and utilizing them in manufacturing could greatly reduce greenhouse emission and carbon footprint. Aside from environmental benefit, mechanical plastic cycling is an economical viable practice, as recycled plastic represent a save of 20 to 50% in terms of market price when compared to virgin counterparts. For promoting the mechanical recycling, various methods have been proposed to promote the quality of recycled plastic, including filler addition, compatibilization, process optimization, and formula design. Most commonly employed preparation method is the melt process due to its advantages such as high efficiency, easy operation, continuity, and industrialization. However, simple blending of inorganic particle with the polymer material, which is practical from the point of view of direct manufacturing of composite particle, is not able to provide the desired homogeneous particle distribution. Clustering consists of highly aggregated particle were generally observed due to high surface energy of the particle and the incompatibility of the chemistry of the surface of nanoparticle with many matrix and polymers. That's why it is necessary to develop the method for effective dispersion of nanofiller in polymer. Thus, following session will represents the studies which have been performed to improve the dispersion and distribution of the nanofillers. The first study is the preparation of carbon black and polypropylene nylon composite with the low percolation threshold using mild blending method. In this study, a new approach, mild blending method, was reported to prepare carbon black filled polypropylene nanocomposite. Carbon black suspension was prepared by dispersing the carbon black powder into deionized water using ultrasonic irradiation for 10 minutes. The intermeshing co-rotating tin screw was used to prepare the nanocomposite. Polypropylene was put into the extruder and melted at 170 degree in the knitting block at the end of feeding section. After that, carbon black suspension was pumped into the second inlet of the extruder and compounded with melting polypropylene in compounding zone. The water content of carbon black suspension was removed from the vent by vacuum to obtain the nanocomposite. Finally, extruder was thermally compressed to prepare sample for complete characterization of nanocomposite. In order to observe the impact of mild blending method on dispersion of filler, carbon black and polypropylene nanocomposite and simple composite of carbon black and polypropylene were analyzed using the SEM analysis. SEM micrograph of the common carbon black and polypropylene composite, as shown in figure A, showed that most particles were aggregated together and aggregation detached from each other. At higher carbon black content, the scale of aggregation increased, which was caused by the connection of carbon black aggregation. The morphological feature of the carbon black and PP nanocomposite during using melt blending method, as shown in figure B, displayed a different structure from conventional carbon black and PP composite. It was observed that carbon black particle were detached from each other at nanometer level with the homogeneous distribution in polymer matrix. Correlation between volume resistivity and carbon black loading for the carbon black and PP nanocomposite and common carbon black and PP is shown in figure C. The carbon black and PP nanocomposite prepared using mild blending method was found to percolate at a threshold of about 2.49 volume percentage of carbon black, whereas common carbon black and polypropylene composite had a percolation threshold of about 7.66 volume percentage. This change in percolation threshold between the two carbon black and PP composite could be explained in light of the dispersion and distribution of carbon black particles. Conductive networks form in common composite at high loading of carbon black due to the close contact of aggregates. The percolation threshold at lower loading of the carbon black in nano composite prepared by the melt blending method could be explained by the tunneling conductivity mechanism. In carbon black and PP nano composite, the carbon particle were dispersed as a primary particle state, located apart from each other and enclosed by the PP, which is an excellent insulator. This arrangement satisfies the requirement of tunneling conduction. When PP contact when carbon black content reached the percolation threshold, the effective tunneling zone of the nearest neighboring particle overlapped and tunneling conduction occurred. Overall, these research show that nano composite can be fabricated successfully by compounding polypropylene with the nano carbon black aqueous suspension using mild blending method. In another research, a novel approach of preparing polymer and nano calcium carbonate composite was presented. A certain amount of nano calcium carbonate particles and ethanol were introduced into the dispersion vessel, and particles were wetted sufficiently by mixing for 10 minutes. Deionized water was added in the vessel, and ultrasonic sonic transmitter was used to break apart the aggregate structure of nano calcium carbonate and uniformly disperse the nanoparticle into the suspension. Then the resulting nano calcium carbonate suspension was injected into the polymer melt in a co-rotating twin screw extruder under pressure through feed tube and a second inlet drilled on the barrel of extruder. The nanoparticles were mixed with the molten polymer and transported ahead. Then the moisture was volatilized from the escape hole, and nanoparticles were held in the matrix at the primary diameter as in the suspension. The extrudate were then pelletized. After drying to remove the attached moisture during the extrusion and pelletizing, the pellet were injected into both dumbbell tensile sample and impact sample. Transmission electron micrograph of the nano calcium carbonate suspension is shown in figure A. Transmission electron microscopy analysis of nano calcium carbonate suspension confirmed the presence of primary size dispersion of nanoparticle in aqueous medium. The clear border of primary particle indicated that particles were cubic and diameter varied from 30 nanometer to 80 nanometer. The dispersion of nano calcium carbonate particle in the matrix were assessed by SEM as shown in figure B, C, D and E. Figure B and D show the SM photograph of nano composite of LLDP and nano calcium carbonate and PP and nano calcium carbonate formed with the normal melt mixing method. The particle aggregation in this material range in length about 0.5 micrometer because the shading factor was not enough to break the nanoparticle aggregation in the melt. The same micrograph of nano composite of LLDP and polypropylene with the nano calcium carbonate formed with the malt mixing method are shown in figure C and E. The nanoscale nano calcium carbonate particle and their perfect alignment with the matrix were observed with the composite formed with the mild mixing method. The mechanical properties of nano composite are listed in table. The tensile and flexural properties of 4 composite are increased with the addition of nano calcium carbonate. However, the impact strength of polycarbonate and polyethylene terephthalate composite showed a slight drop with the addition of nano calcium carbonate. It can be concluded that mild blending method is feasible for preparing both non-polar polymer and inorganic particle, or polar polymer and inorganic particle in nanocomposite. Thermal degradation didn't occur even if water was introduced into the melt. Especially compared to neat PP, iso impact strength and the tensile strength for PP and nano calcium carbonate composite showed a substantial increase with the addition of only 1.5 weight percentage of nano calcium carbonate particles. It suggested that organic nanoparticle with good dispersion state obtained by mild mixing method can play an important role in improving the strength and toughness of PP. The result demonstrated that nanoparticle in all four kind of matrix are in form of primary particle, and this novel technology called the mild mixing method is appropriate for not only non-polar polymer but also polar polymers. Next is dynamic injection molding. In this research, carbon black was premixed with polypropylene pellets in mixer for 10 minutes in various ratios, and that fed into the tri-extruder operating at a screw speed of 90 rpm. The resulting extrudate was cooled in water and cut into pellet using pelletizer. The extruded pellets were grinded again in a vacuum oven. Standard samples were molded via custom-made electromagnetic dynamic injection molding machine as shown in figure. Electromagnetic applied vibration with different frequency to study the effect of electromagnetic vibration forces. Morphological analysis was performed to study the effect of electromagnetic forces on the dispersion and distribution of carbon black nanofiller. Micrograph of SEM analysis shown in figure A and B. Figure A shows that micrograph of carbon black and polypropylene nanocomposite without any application of vibration force. It can be seen that distance between carbon black and nanoparticle is large with no vibration, and carbon black particle have no obvious agglomeration phenomena in the matrix. The density of particle distribution is not big enough to the formation of conductive network because particle can aggregate easily in the molding processing. Figure B shows a micrograph of the carbon black and polypropylene nanocomposite with the application of vibration force. It can be seen that dispersion of carbon black particle in matrix has improved significantly. The average particle size of carbon black particle decreased greatly because of the blending of the melt enhanced. The vibration force has direct influence on the internal structure and the microstructure of the products. Polymer is compressed and released periodically with different vibration amplitudes and frequency under the effect of vibration force. It is beneficial to dispersion of particle and the formation of conducting network structure. Figure show the electrical conductivity and shielding effectiveness of composite with different loading of carbon black. The electrical conductivity and shielding effectiveness of carbon black and PP composite increase with the loading of carbon black changing from 10 weight percentage to 30 weight percentage. The electrical conductivity of composite show a dramatic increase of 10 order of magnitude as the loading increase from 15 weight percentage to 20 weight percentage, indicating a percolating phenomena. Carbon black have been condensed to a special chain structure and produce a large number of conductive chains and branches. After applying vibration fees fall to the injection molding process, the rising trend of electrical conductivity is similar with the result of no vibration. Compared with the no vibration, the electrical conductivity has great increase when the content of carbon black is more than 50 weight percent because of introduction of vibration force field. Overall research on the properties of PP and composite products by dynamic injection molding showed that the introduction of vibration force field could effectively improve the dispersion of filler and differences of electrical conductive distribution in different parts of the composites. Next is solid state drying of post-consumer isotactic polypropylene. In this search, the 1.5 percentage of carbon black and isotactic polypropylene pellets were premixed before the polymer processing step. All isotactic polypropylene grades were processed by using a single screw extruder attached to a melt pump and a tape die of 15 millimeter width and 1 mm height. Filtration was achieved with filter of different mesh sizes ranging from 80 micrometer to 250 micrometer. The tape were quenched with the chilled rolls and a drying line with 4 controllable induction heated roller sets and 2 induction heated oven were used. The oriented tape were wounded onto a bobbin and used for further characterization. The fact of mesh size and carbon black is presented in the table. It can be observed that for Vision PP, the addition of carbon black result in reduced draw ratio. By the addition of carbon black, the maximum attainable draw ratio is lower since this acts as a contaminant. The addition of carbon black to recycled isotactic polypropylene show the opposite effect. In polyethylene and isotactic polypropylene blend, the carbon reside in the polyethylene phase without significantly affecting the viscoelastic or thermal properties of blend. In the solid state drying process, the result in a better process stability by improved stress transfer between the isotactic polypropylene matrix and the PP contaminants. The addition of carbon black to recycled PP resulted in higher attainable maximum draw ratio for recycled isotactic polypropylene. Looking at the material without carbon black in table, it can be observed that maximum attainable draw ratio decrease with decreasing mesh size for recycled isotactic polypropylene. It is clear that presence of solid particle which act as stress concentrator is the limiting factor in this experiment. A fine mesh contribute to more stable process operation and high draw ratio. The effect of melt filter mesh size on the mechanical properties is shown in figure A, B, C and D. For both unfilled and carbon black filled material, the elastic modulus and tensile strength are not directly affected by the size of the mesh, but they can be drawn further, yielding drawn tapes with enhanced properties. The maximum tensile strength of 385 megapixel was obtained for post-consumer filled polypropylene with 80 mesh filter at 18 draw ratio, which is an improvement of 15 times compared to the isotropic tensile strength of 20 megapascal. Figure A and B shows the evaluation of crystallinity for unfilled material and carbon black filled material, both as a function of draw ratio. The crystallinity increases with the increasing draw ratio, and the crystallinity of recycled material is lower than the virgin isotactic polypropylene. Focusing on the differences between recycled material, it is seen that melt filtration size doesn't affect the crystallinity. Filter separate solid particles such as PET of size much greater than the laminar thickness. Therefore, the crystal formation is not hindered. Overall, this study presented the potential of solid state drying process, which significantly enhances the process of recycled isotactic polypropylene. It can be concluded that mild blending method, injection molding, dynamic injection molding and solid state drying method improve the properties of nanofiller reinforced polymers. Mild blending method improves the properties of polymer which are not affected by the water but can cause to degrade the hygroscopic polymers. Solid state drying method enhances the properties of filled polymer by improving the crystallinity and chain orientation of polymer matrix, but the utilization of drying line make it complex and expensive operation. Now I will present the novel method of preparing the polypropylene and carbon black nanocomposite with the aid of ultrasonication and application of high temperature mixing. This research is being done at the Department of Polymer and Process Engineering, UT Lahore, under the supervision of Dr. Yasir Kumgil. In the first step, waste non-woven polypropylene will be compacted in a vertical compression molding to make thick sheet, because Soft fabric cannot be shredded using a small industrial shredder. This hard and thick sheet will be taken to a small scale industrial shredder with high speed sharp rotating blade to reduce the size of the sheet for the next step. In the next step, the coarser particle obtained will be grounded in a small high speed rotating blade grinder to further reduce their sizes. The powder polypropylene will be combined with the carbon black nano filler with the help of sonication in a sealed container at high temperature and pressure to enhance the mixing. After complete drying, the mixture of carbon black and PP powder will be blended into a scale lab small scale uh, s- uh, uh, small scale single screw extruder. The resulting extruder will be size reduced using a shredder and milling machine. The resulting powder will be molded using a lab scale vertical compression molding machine into a square sheet, which will be cut into the specimen for testing purposes. The sample will be characterized using FTIR, DSC, TGA, flammability testing, UV degradation studies, HDT, MFI, optical microscopy, ISOT impact testing, uh, 3-point bending testing, and SEM analysis. The carbon black nanofiller is expected to improve the chemical, mechanical, rheological, and thermal characteristics of reclaimed non-1 pp industrial fabrics. It is expected that properties of resulting polypropylene will be comparable to commercial available grade of polypropylene being used in automobile industries. In addition to the automobile component, the modified polypropylene waste could be utilized in a variety of applications, including electronic devices, casing, hardware accessories, non-food grade container, and so on. This will not only save the environment but also provide a cost-effective solution to the plastic raw materials. Uh, Here are references for the study presented, and that's it.